we introduce efficient event-based object detection, a hybrid SNN-ANN neural network with spatial and temporal attention. Event cameras operate differently from traditional frame-based cameras. Instead of capturing full frames at fixed intervals, they asynchronously record changes in pixel intensity at a microsecond resolution. This high temporal resolution enables the capture of fast motion, making event cameras ideal for high-speed tracking and object detection tasks. Additionally, event cameras offer a significantly higher dynamic range compared to conventional frame-based cameras, allowing them to perform well in challenging lighting conditions, as demonstrated here. As mentioned, event cameras have microsecond-level temporal resolution and produce spatially sparse outputs. In real-world tasks like object detection, the scene usually changes at a slower rate in the range of milliseconds. Processing this high-speed, spatially sparse data with traditional ANN-based architectures is often inefficient and impractical in certain scenarios. However, these sparse event signals contain rich temporal information that can significantly improve our understanding of the scene. Therefore, we design a hybrid network that combines an efficient spiking neural network to process sparse and high temporal information effectively, followed by an artificial neural network component that operates at a lower frequency for accurate task prediction. To bridge the SNN and ANN components of the multi-frequency network and convert the output of the SNN layers into a denser representation, we propose an attention-based SNN-ANN bridge module. This module transforms temporal and spatially sparse inputs into a denser, lower-frequency representation. The attention-based SNN-ANN bridge module consists of two subcomponents: spatial-aware temporal attention and event-rate spatial attention. These attention mechanisms work together to refine the sparse event data by focusing on important spatial and temporal features. The output from the attention module is then passed to the ANN layers for further high-level feature extraction. Finally, the processed features go through a detection head to predict object locations and classes. Here is a visualization of our hybrid multi-frequency network, where different parts of the network can operate at different frequencies. We demonstrate two variants, one with a depth-wise separable convolutional LSTM to capture slow temporal features, RNN variant, and another without the LSTM that runs at a lower frequency, without long-term information flow between ANN components. Let's dive into the details of the attention-based SNN-ANN bridge module, starting with the spatial-aware temporal SAT attention module. The first part is channel-wise temporal grouping, which groups together features that are temporally related to improve temporal understanding. As shown in the toy example, mid-level features from different time steps are grouped together. These grouped features are then passed to the next module, called time-wise separable deformable convolution. Time-wise separable deformable convolution uses deformable kernels to efficiently capture sparse spatial information. It models the spatial context for each temporal group separately, which is why it is called time-wise separable. An example of a deformable kernel is shown on the right, where the green grid represents a standard convolution kernel and the red grid represents a deformable kernel. The time-wise separable features are passed to a temporal attention module, which extracts temporal features by applying self-attention along the temporal dimension. The next component is event-rate spatial attention. Here we take the output from the SNN blocks and calculate the event firing rates over time. A sigmoid function is then applied to generate spatial weights. These weights are used for element-wise multiplication with the output of the SAT module, assigning higher weights to regions with more activity and lower weights to less active areas. We have evaluated our approach against various state-of-the-art methods, including ANN-based, SNN-based, and RNN-based models, using the Prophecy Gen 1 and Gen 4 automotive datasets. The results show that our approach outperforms all SNN and ANN-based methods and achieves performance comparable to RNN-based approaches. To demonstrate the viability of our hybrid approach, we implemented the SNN blocks on the Intel Loihi 2 neuromorphic chip. The experiments show that the SNN blocks are significantly more efficient in terms of power consumption and latency when deployed on neuromorphic hardware, as shown in the table. We also evaluated the network's performance at different quantization levels of the SNN blocks for hardware implementation, which revealed negligible accuracy drop, as shown here. We also compared max, multiply accumulate operations, and ACs, accumulate operations, across different network variants and different approaches to highlight the computational efficiency of our method. Moreover, we analyzed power consumption and found that the proposed method achieves a better balance between accuracy and energy efficiency. An in-depth ablation study was conducted on each component of the proposed ASAB module, along with various configurations of the hybrid architecture. Visual results comparing models with and without the attention-based SNN and ANN bridge module demonstrate more robust predictions and significantly fewer false detections. For more details, please scan the QR code. Thank you for your attention.